Greetings, this is Rick Powers making a video for Basic Statistics, Lesson 16. Hello, this is Rick Powers from Western Technical College, Basic Statistics. Lesson 16, Binomial Distribution, Part 1. Consider the following situation. I have a class of 25 students, and I want to think about how many of them like soccer. But I'm not simply going to ask them. I want to consider what to expect. In other words, I want to know something about probabilities. Now consider this situation. I toss 10 coins on a table, and I want to think about how many of them will come up to be heads. These situations are related based on a couple of ideas, and these ideas will be foundational to some important aspects of statistics. Both of these situations are examples of binomial probability. It's called binomial because there are only two outcomes. For the coins, it's heads or tails. For the students, I limit the responses so that they can either answer yes or no. The binomial nature of the problem requires us to define success. That can be a bit misleading. Maybe we're asking about having a serious injury. So that's not a success in normal terms. But saying, yes, I have been injured would be an answer that we are looking for. But there is a major idea that must be kept in mind. What are we measuring? And the answer is we are measuring the number of successes out of a set number of observations. The number of successes is X, and the number of observations is N. Example, for the coins, N is equal to 10, and the number out of the 10 that would come up heads is X. For the students, N is equal to 25, and the number out of the 25 who would say, yes, I like soccer, is X. However, there is a third number that is required when we consider binomial distributions. It's a bit strange, but it is required. Before we use the binomial distribution, we have to be given a general probability of success, which is applied to each individual. We use the symbol P, note lowercase, to indicate this number. It seems logical to think the probability of getting heads for each coin is 50%. For the students, we have to be given a general probability, usually from a national survey or similar information. In order for us to apply mathematical formulas to this situation, we have to assume that each individual is the same and that each person does not affect anyone else. That's not completely true, but we have to limit our ideas in order to apply them. Every science has to do that. So then, if there's a national survey that says 30% of people like soccer, then we assume that P is equal to 0.30. For every binomial problem, we must have these three numbers, N, X, and P. Often we have multiple possible values of X, but N and P are fixed. To review, I am measuring the number of successes, X, but I want to know the probability of all possible values of X before I actually do the survey. The result of finding the binomial distribution is then a discrete probability distribution because X has only a whole number of values. Now I will go over how the mathematics works for this and then give the formula. But just as with earlier formulas, we have technology to give us the results, which is often easier and more accurate. Recall that we multiply probabilities when we make choices. So if I have 25 students, then I need to consider multiplying the probabilities 25 times. Example, what if all 25 students said yes? That would be 0.30 to the 25th power, which is about 0. If all 25 students said no, then that's 0.7 to the 25th, which is approximately 0.00013, which is still small. So there must be something in between. In order to find out, say, what are the chances of having 8 people say yes, then clearly we would have 17 people say no, but we also have to consider how many ways that can happen. It could be the first 8, or the last 8, or some other combination. Aha, that's what we need, the number of combinations. So here's what we have. Probability of 8 is equal to 25C8 times 0.3 to the 8th times 0.7 to the 17th. So then the probability of 8 successes is found by multiplying the number of possible combinations times the general probability of success to the 8th power times the general probability of failure to the 17th power. This answer is about 16.5%. Now I have a little glimpse of what if my general probability holds true and I ask 25 students if they like soccer, then I have a 16.5% chance of having 8 students say yes. Seems like we're getting somewhere, but it would be nice to have more information. Here's a graph created by technology. Note that we can find unusual values of x by looking at where the probability is less than 5%. The graph then shows the probability on the vertical axis, the values of x on the horizontal axis, and we have n is equal to 25, general probability p is 0.3, and we know that the probability that x is equal to 8 is 0.165, etc. Now we have good info. I expect to have between 4 and 11 students say yes. If there were 0 to 3 or 12 or more, I would be surprised. In the next lesson, we will go through this last subject in greater detail and connect the empirical rule with the bell-shaped results that we often use. End of lesson 16.